Hello, this is Mrs. Johnson. This is MAT221. This is section 3.9, talking about linear approximations and differentials. So we've talked about logarithmic differentiation in the last section. Now we're going to go on and talk about the linear approximation. Now, let's talk about the concept of where this comes from. For any function f of x, the tangent line to the curve is a close approximation of the value of the function for some small distance from that point of tangency. In other words, if we have the blue curve here, and we're talking about the tangent line to the curve at x equals a, which is right here, we could find the tangent line to the curve using our linear equation for finding the tangent line, y equals m times x minus x1 plus y1, which is Euclid's formula for the equation of a line at any point on the coordinate plane. And if you notice that the tangent line to the curve and the actual value of the y value of the curve are very close to each other near the point of tangency. So what Leibniz and Newton were saying was that if you look and we zoom in close enough, the value of the line, the tangent line, and the value of the curve are going to look a lot alike if we zoomed in close enough to that point. So in the days before calculators and computers, they used this process of what's called the linearization, or in other words, use the tangent line to the curve to estimate the actual value of the curve, the output of the curve, near the point of tangency, so that you wouldn't have to put your value over and over again into the curve at a given point if you were near that point of tangency, especially if the curve was quite complicated, something like a natural log, which was before calculators or computers could be quite difficult to calculate that without a slide rule or some other type of mathematical interpretation. So we call the equation of the tangent line to the curve the linearization of the function at that point of tangency. It is called what we call the line that mimics the curve at that point. So we're going to start with the point slope equation of a line, and we're going to just rewrite this and say, okay, what does this look like? So if we rewrite what we have here in my equation, my point slope equation of a line, and say, okay, the value that I'm looking at, the point of tangency, the x coordinate is equal to a. The y coordinate of the point of tangency, which is y1, would be the value of the function at a. And the slope of the curve there is going to be the derivative at a, which is, we know what that is, what's called the slope of the curve is called the derivative at that point. So if we went back to this curve, we could say, okay, so in other words, x is equal to the x coordinate of the point of tangency. The y coordinate at the point of tangency, which is y1, would be the value of the function there. And the slope of the tangent line to the curve is the derivative of the curve at that point. All right, with those substitutions, let's substitute those into Euclid's equation for a line, point slope form of a line. We get this equation. And when we bring the y coordinate over to the other side, we get this. Notice this equation and the top equation, Euclid's equation, and this equation are actually exactly the same. It's just that Leibniz and Newton were using this new notation, using the derivative notation that they came up with, to rewrite Euclid's formula in this form. Now, often when I write this formula, I actually write it as slope, or f prime at a, x minus a plus f at a. I usually bring this y coordinate to the other side. But this is the way the book does it, so I'm going to leave it this way for now. This is called the linearization of the function at x equals a. In other words, this is just like the formula for finding the equation of the tangent line to the curve that we've been doing all semester. It is called the linearization, or the linear approximation of the value of the function at near A. So what Newton and Leibniz said was that the value of the function, the actual output of the function, is very close to this tangent line output near the point of tangency. So we're going to use the tangent line to approximate the value of the output of the curve near the point of tangency. So the linearization is the equation of the tangent line to the curve, and if you like this old formula better, you can simply use that formula again. You absolutely can. It's just I want you to notice how the two formulas are exactly the same, just manipulated with function notation, giving derivative notation here. So wherever we see the slope, that is actually the derivative. Where we see f at a, that's actually the value of the function y1 at the point of tangency. And where we see a is the value of the x-coordinate at the point of tangency. All right, that said, let's look at a couple other things here. If a function is concave down on an interval, then we know that the tangent line to the curve will be above the curve. Therefore, we say that the tangent line approximation, or the linearization, is going to be an overestimate of the actual value of the curve if the curve we're looking at is concave down. Now this makes sense because if you look near the point of tangency, we're going to be using the tangent line to approximate the y value of the curve near the point of tangency. So if I looked right here, I'm sorry, let me go backwards. If I looked right here at this value right here, you'd notice that the value of the line and the value of the curve at that same x value, the tangent line is above the curve, so it's going to be a tiny bit bigger than the actual value of the curve. Same thing over here. If I took a point over here and I said I'm going to use the linearization, or the line, as an approximation to the curve, notice that the line is a little bit above, so the y value of the line is a little bit above the value of the curve, again, near the point of tangency. Now notice Leibniz and Newton said that this only works if we're near the point of tangency, which again is very relative to the curve. Notice the farther I go away from the point of tangency, the value of the line and the value of the curve are not going to be a good approximation. So we say that this approximation is only going to be a good approximation if we're near the point of tangency. Notice again, the farther I go from either side, from the value of the point of tangency, the value of the line and the value of the curve are not going to match each other. They're not going to be a good approximation. But the closer I get to the point of tangency, you can notice that the line and the curve will be very good approximation for each other, for their outputs. Again, that same concept, if the function is concave up over an interval, the tangent line to the curve will be below the curve. Therefore, the tangent line approximation, or the linearization that we're going to find, will be an underestimate to the actual value of the curve. Again, you can see that if we use a line as our approximation to the curve, the y value of the line and the y value of the curve will be almost the same, but the linearization, or the line value, will be a little bit of an underestimate to the actual value of the curve. And just as before, the farther away I go from my point of tangency, the farther away my y value. Look, my y value will be an underestimate, but a big underestimate the farther away I am from the point of tangency. So if I'm near the point of tangency, my line is a good approximation to the value of the function near the point of tangency. We're going to also just talk about a little bit about the concept of a differential. Now, a differential, when we first started talking about derivatives, we used Leibniz notation, and we did this also with implicit differentiation. We said that it is delta y over delta x, which became Leibniz notation of the derivative of y with respect to x. Now, when we look at this, it's really the change in x over the change in y. And if we look at this notation was not allowed to be separated because it was just meant the derivative of the curve at x equals some point. It is the derivative of the function with respect to x. And we just used this whole notation, and we weren't allowed to use it as a fraction. However, Newton and Leibniz said it actually is beneficial to us as we move forward to think of this as a very small change in y over a very small change in x. And if I had a very small change in y and a very small change in x, then I could take these two pieces apart. And they had to come up with a name of what each of these pieces were called. Each piece of Leibniz notation became called a differential. Now, there is an entire course on differentials. Actually, it is Calculus 4. It is called Differential Equations. There's an entire course, an entire semester talking about differentials. In Calc 1, we're just going to brush the surface here to introduce the concept of what these differentials are. So what it is we say that the derivative expression dy over dx can be thought of as two separate pieces as long as there is a very small change in x and a very small change in y. Now, Leibniz and Newton on purpose let this be a little bit ambiguous because a very small change is all relative to what we're talking about. For instance, if we're talking about miles in outer space, 1,000,000 miles might be actually a very small change in x when we're talking about multiple millions of miles in space. So when we talk about nanotechnology and chemistry, when we're talking about really small changes in grams, then a 0.001 gram might be a very small change. So again, it depends, it is relative to what we're talking about in context to each problem. However, Newton said if we have a very small change in y and a very small change in x, then we can take this notation apart, and each piece, dy and dx, are called a differential. So dy can now be considered a very small change in y, and dx can be considered a very small change in x. Each piece is now called a differential. When we put the pieces together, we still bring it back to the derivative of y with respect to x. So if I said to you, let y equals f of x be a differentiable function, then the differential dx is considered the independent variable, and the differential dy is considered dy equals the derivative of the f function with respect to x multiplied by dx. In other words, what we did here is we took the two notations, Leibniz notation of dy dx, set it equal to Newton's notation, which is f prime of x. But now if we think of dy and dx as small changes of x and y, we can then cross multiply and get this new differential equation, dy is equal to the derivative of f multiplied by that very small change in x. So let me give you an example of how we would use these differentials. And again, we're just brushing the surface here in Calc 1. When we get through Calc 2 and 3 and get into differential equations in Calc 4, these will be much more explored to a higher degree. So let's look. Consider the circle of radius 10. If the radius increases by 0.01, approximately how much will the area change? Now, the first thing we're going to look at here is, do we have a very small change? So it says if the radius is increasing, so here's a rate of change by 0.01. Now, if you think of a radius of 10, then a change of 0.1 is a relatively small change in my radius. So I'm looking at my change in my input, which is radius in this case, is a very small change. So I can use a differential equation here. So what we're going to do is we're going to say, okay, we want to analyze the area. So we say, okay, what is the area of a circle? The area of a circle is pi r squared. Now, if I took the derivative of this expression with respect to r, so I'm taking the derivative of the area with respect to the radius r, that is dA dr, it's going to equal, if we use our rules, this pi is a constant. We're going to drop this to the front. That's the power rule. So I would get 2 pi r. By the way, I do want you to notice that the derivative of the area of a circle is equal to, this is actually the circumference, right? 2 pi r. that being said, remember, if dr is a very small change and we want to know approximately what is the very small change in the area,